It's my pleasure to welcome you all on behalf of the QIR Alliance to our session today. We do have, as you heard, a range of speakers that I'm very honored to get the pleasure of introducing. We've got Pete now from Quantinum, so recently just had a company combination and hence the rename compared to what's on the agenda. Pete is a compiler engineer at Quantinum with a background in programming language theory. Then we've got Tom, who after a career of 37 years of being the president and CEO of his own company, is now the chief software architect at Quantum Circuit Incorporated. We've got Kalan, who took his first programming course in elementary school and later became a captain in the US Army, a security analyst, then joined Amazon Web Services and is now the director of software engineering at Rigetti Computing. We've got Chris here, our resident quantum algorithms expert at Azure Quantum and book author. And last but not least, on the slide, you also see Travis Humble, the Deputy Director of the Quantum Science Center, who unfortunately, due to policy reasons, cannot join us in person, but will be joining us virtually, so to speak, in the form of a video as part of the presentation. Now, I'm Bettina. I'm the steering committee chair of the QIR Alliance, which you have either already heard of, or I hope you're now curious what it is. In either case, I will tell you more about the QIR Alliance towards the end of the session. But first things first, talking about the goals and ideas and aspirations is all good and nice, but what really matters ultimately is what we can achieve. So hence, without further delay, we will first jump into 3 proofs of concepts that we have prepared for you to illustrate what we have accomplished working together over the course of the last year or longer in some cases. Today, what we're going to see are the next steps in quantum computing. We hope to define a quantum intermediate representation that permits to unlock the full potential of quantum processors. To that effect, we'll present 3 demos running on 3 different hardware backends. For each demonstration, we'll focus on particular points that we think are valuable going forward for quantum computing as a field. Now, we don't want to repeat ourselves. It's a short time with a lot of very interesting content. So we will focus on particular aspects, but that doesn't imply that these capabilities or features don't apply to other hardware platforms. We will also show you recordings of the submissions for the first 2 ones, because in some cases, these demos actually involve collecting quite a bit of data. So think of it like the cooking show, where we present you the submission and then ready, pre-baked comes out the result, and we're going to be talking about that. All right, and with that, let's jump into the first one. That's going to be a demo that presents a step towards fault tolerance. And we're going to be illustrating arbitrary control flow and full program optimization as part of that demonstration. We'll then proceed and go 1 step further and also think about what we could do if we additionally had the ability to perform classical computations as part of quantum execution. This will lead us to really a new way of thinking about quantum algorithms. And then in our 3rd demo, finally, we'll apply this and think about what that means for today's ecosystem of quantum offerings and quantum cloud offerings also in particular. So we will be looking into an automated approach to enable high-performance quantum computing, so to speak. And we will focus on the aspect of having the option for a provider to optimize a hybrid computation. Starting with the first aspect, a step towards fault tolerance, we will be showing you a magic state distillation running on the Quantinum H1 processor powered by Honeywell.
So many things are true of near-term and small-scale quantum devices that we don't expect to be true of scalable or fault-tolerant quantum devices. On near-term devices, we'll often work directly with things like rotation gates, where we can pick whatever arbitrary angles we like to feed into our rotations. But as we move to scalable and fault-tolerant devices, we can reduce that noise arbitrarily at the cost that we then need to synthesize those arbitrary rotations in terms of the simpler gates that we can protect with error correction. So one way to do that is to use magic state distillation to make high fidelity copies of magic states that we can use to do that synthesis. Magic state distillation doesn't always succeed, however, so we need to be able to loop over distillation attempts to get a good enough copy that we can use in synthesis. That tells us that real-time control flow is a necessary step on the path toward achieving fault tolerance. So let's take a closer look at how QIR can help us take that step.
So we're going to be talking about running magic state distillation on Quantinuum hardware. And in general, we're very excited to take QIR as a new input for our compiler. And so what we want to demonstrate here is a couple of things. One, that as we submit to our emulator and to our Quantinuum hardware, that we meet the ideal expectation value bars on the figure on the right-hand side on both the emulator and on our hardware run. And secondly, to show just how easy it is via Q# and QIR to recompile the magic state distillation to use different depths and to do measurements across the X, Y, and Z bases. And so just demonstrating how easy we can rapidly prototype on the emulator and then move to running on real hardware and kind of verify that the results are consistent. So one of the main goals with support for QIR was to allow more expressive and powerful programs and applications to be running on Quantinuum quantum computers. And so before, we generally had flat CASM2 programs that were submittable to our quantum computers, with some conditionally applied gates and so on and so forth. But with QIR, we have more expressive control flow that's possible. And so with magic state distillation, as we compile across different iterations, you basically have a different number of runs that you can do that are compiled differently. And within each iteration, you can have basically nested conditional branching with true or false kinds of logic and exit points for your program. So this is really kind of increasing the expressivity of the algorithms that can be submitted to our quantum computers. And in the process of supporting QIR, we're still showing on our hardware that, we're doing mid-circuit measurement, qubit reuse. Beyond the initial QIR compilation, we kind of plumb all of the different things necessary for moving around ions and doing transport and various other things. That's not in the QIR itself. It's all stuff that's just part of our compilation process. And now we're supporting these nested conditionals and classical function calls as well. And so with this video right here, what we're wanting to demonstrate is that we have our distillation program on the left, where there is a Q# program with recursion and a branch within that recursion, so much more expressive control flow. It was just submitted by a user to our simulator with 10,000 shot counts. They're now looking at the results for that, kind of verifying that things are correct. And what's going to happen now is that after verifying that the results look correct in the emulator, now the shot count is being lowered to 1,000 and the target is being changed from the emulator to the actual H12 target. And it's just a seamless process, pretty much repeating the same command and just kind of changing a couple of things. Then after that, verifying that the results look consistent is the exact same as getting results back from the emulator as well. And so that's the last step of this process right here. So let's actually talk about the emulation results for magic state distillation. We said we wanted to meet these kinds of ideal bars here on the right. And with rapid prototyping and recompilation for each distillation depth, it was just a small couple of changes to basically recompile and submit these programs. And then after submitting all of the different versions, we see exactly what we want. So on the emulated results, we see that we have very similar results in each basis. the emulation results approach the ideal bars across each iteration count. And in general, as the distillation depth increases, the results get better and better, which is what we wanted to see. So after achieving confidence in emulation result with this rapid prototyping approach, like we just saw, it's really easy to submit to Quantinuum hardware after that. And so with the hardware run and results, we could see that the results for our emulator and our hardware really are at parity. So as soon as you're submitting to the emulator, you're getting really confident feelings that you can just go ahead and submit to hardware and you're going to get the same results that you expect, but with like a real proof of concept. And so we see hardware similarly performs better with higher iteration counts. We're meeting the ideal result bars, similar things in the X, Y, and Z bases as well. And the hardware and emulation similarities because the emulator has a kind of precisely tuned noise model for the hardware. So the noise that's in the emulator is going to accurately basically show what's happening on hardware with our results. So there's some key takeaways I wanted to get at here. So with QIR, we wanted to have more expressive control flow, expressible in programs that could be submitted to our machines so that certain applications or experiments like magic state distillation can be submitted to our hardware. Supporting QIR really makes it nice for Q# programmers just to like rapidly prototype, kind of change a couple of lines of code, and then get quick emulation results before going on to hardware. And finally, that the emulator and the hardware at parity for both language supports. If it's running on the emulator, it'll run on the hardware. There should be no gotchas there. It should be seamless. And the final thing I wanted to say beyond that is that we're very excited to, take in QIR as a kind of first-class focus for the compilation stack going forward. And so in general for Quantinuum hardware, we're going to be looking at, this kind of QIR-based, but also LLVM-IR-based compilation stack in general, and really pushing the capabilities of these machines at Quantinuum. Back to you, Bettina.
All right, as promised, we are going to take it one step further. Now we've seen what we can do if we have things like arbitrary control flow and what that can enable working with. Now, what if we also had the option to perform classical computations as part of the quantum execution?
So to do that, we'll talk about random walk phase estimation running on QCI hardware. And to kind of take a step back, consider if you're running a chemistry application, for instance, finding the ground state energy of some electronic structure problem. Then you have a couple choices that you can make at this point. You could do something like run a variational quantum eigensolver, where low-depth circuits are ideal for fitting within the constraints imposed by noise and current devices. But that comes with some trade-offs. You can't reuse state preparation, so you have to re-prepare the state in every iteration and every measurement, and you give up the 1/n scaling and get back to the standard quantum limit of 1/n. On the other hand, you might consider something like iterative phase estimation closer to what we might do on a fault-tolerant or scalable device. And there, we get to reuse the state preparation across iterations and across measurements. We get the 1/n scaling, giving us improved accuracy, but it's really impractical to run on current devices due to the large depths that are just hard for current devices. So what we really want to be able to do is integrate these two approaches and interpolate between these different trade-offs. So there we want something where we have the low-depth kind of circuits that can fit in near-term devices. And one way to do that is by resetting only when we need to. And we can do that by tracking our estimate of the phase online. Now, if I decide to do that using, for instance, a lookup table that might be traditional now, using around 60 measurements would be fairly typical for a phase estimation-based approach. So I'd need to write down what phase is my current estimate in each of the 2 to the 60 different branches of that algorithm, which is already exabyte scale data and completely impractical for embedding in a quantum program. On the other hand, if we have the ability to track our current estimate of the phase as a classical variable in the execution of that program, then we can do some really cool stuff. So let's see how QIR helps us out with that.
Alrighty, well, ask and you shall receive. So our team at Quantum Circuits has been working with Microsoft for the last, did I somehow go to the wrong place? There we go. We've been working with Microsoft over the last year and a half, and they've done some fantastic work to basically integrate with the QIR, but also to explore the ways in which the QIR enables quantum circuits to expose some of the unique characteristics of our hardware through QIR. And that's what we'll be talking about today. In particular, the ability to execute the classical calculations right inside the quantum program. And that is pretty new in this business, as you know. So I'll be using here a random walk phase estimation algorithm as a demonstration. And in this example, we wrote it in Q#. That gets translated to QIR. And in that circuit, think of this box on the outside here as the complete quantum circuit. It includes both a quantum subroutine, the green box there, that accepts some angle parameters, and then, but it also includes the classical subroutine code that can perform some calculations based on the measurements that you get back from that quantum subroutine. And then what happens is when you do that, you can then go into a loop check, and perhaps it's a run until success algorithm, or perhaps you want to do 24 iterations. But you loop back, and basically what you're doing is you have an iterative algorithm which is being executed while the qubits are coherent, and it's adapting its angles and other variables in the circuit based on the measurements that it receives. So this is fundamentally different from the way algorithms are assembled now. So I'm going to show you here. We've run this on the actual QCI hardware. And let's see, I have to launch it. There we go. So we're launching the program on Azure Quantum. We're going to be executing 5,000 shots in this program. You can see on the left, this is a typical Q# program. One of the fundamental goals of Q# was to include the quantum and the classical computation in the same program. And we've done that here. Now, what's unique, though, is that if you look, you can see that there are some calculations being done in this Q# program. That's what's basically new. Now, when this program completes at the end, what you'll see is we get back our expected distribution where you see your answer. But what is interesting is that this was all done in one program execution with multiple iterations, making some adjustments to the angles inside the circuit itself. A very new thing in quantum computing. So essentially what we're doing is we're taking the best of both worlds. We're taking this ability to iterate. We're also taking this ability to adapt the circuit and do reset when needed in order to create these circuits that have lower depth. We can reuse the state across iterations. And here what we're doing is we did an additional experiment where we explored the various trade-offs. Do you get better results if you do different number of iterations before resetting? And you can see here we got a nice peek in the data there. Now, in the end, what does this do for the user? Well, you get smaller programs. They don't have to be as long because they're compressed down and they're in a loop. Ultimately, we have faster program execution because you don't have to go back and forth between the classical and the quantum to execute. And ultimately, this introduces a whole new class of algorithm design patterns that haven't really been explored before. And that's what we think is really exciting that the QIR brings. Give it back to Bettina now.
So now we've heard and seen quite a lot about what interesting new opportunities we can explore in the future. And let's now relate that to how quantum computing is used today. And as you know, we rarely have a quantum computer in our basement, unless you're lucky. The other people will need to submit their quantum programs to a cloud provider, where it then gets ultimately forwarded to an actual quantum processor. And we've seen a certain evolution in the last couple of months or maybe years from initially having the setup where large pieces of the program logic were written in a classical framework like Python, for example, that was then executed on the client machine to produce effectively the quantum program itself. And that was then sent up to a cloud provider and forwarded to the actual quantum processor where it ran. Now we've seen we have a lot more options for an integrated approach here. And one of the interesting aspects about that is that we can now also have the cloud provider, or rather the actual hardware provider, determine how to best execute that particular program. And so we're going to be hearing more about that as part of our third demo.
Thanks, Bettina. So today, you want to run a quantum program. How do you do it? Usually some kind of Python script, right? Qiskit, Circ, PyQuil. And that's usually easy enough, right? Especially if you're familiar with Python. But when you think about it, when you step back and think about it, that comes with a lot of heavy weight, right? You're carrying a lot with you. That Python runtime is allowing you to assemble your program, serializing it, shipping it over the network, awaiting results, and then packaging those results, and then you use Python to process those somehow. Maybe you do that in an iterative loop. It's hybrid computation, and that's a use case that's near and dear to our hearts at Rigetti. But your code doesn't own its vehicle, it's renting, right? You rely on that runtime, and that needs to be provided one way or another, maybe in a Jupyter notebook in a container or something like that. The difference is with QIR, it's the whole deal. It's classical runtime, it's your quantum instructions, and the importance of that is that the line between those can move around. Between platform to platform, or even on one platform over time, what can happen in the real-time system versus the near-time system might move. And even on one platform, even if you have a fancy ASIC that has a real rich instruction set, that might not mean that you want to do all of your classical heavy computation right there on the real-time system. It might be faster to do it somewhere else. So the advantage that QIR brings is that the compiler gets to make that decision for you. And so I want to start off here. This is a PyQuil program. So that's that classical runtime that I was talking about. It's what most folks are used to writing their programs as. And you have to decide kind of what runs where. Your classical instructions set up your program. You define a quantum program. You ship that over the network. And then you perform a reduction operation afterwards on your near-time system, maybe in your Jupyter container. This is the equivalent of that program, or the important bits, in QIR. So you can see those QIR intrinsic operations, so those would be your quantum instructions and those that are related, like reading out results. You've got some arbitrary reduction operations, classical instructions, and a shot count loop. Now the syntax may not be familiar to a lot of folks, but this is LOVMIR, right? There's decades of experience around optimizing this, manipulating this kind of structure. And what I want to show today is how we, with the Rigetti QCS integration, help make that decision for you. So we take your input program like this, which could have come from any front end that supports QIR. We'll see Q# here in the demo. And we'll manipulate and transform that program so that the right things run in the right places. And as we improve our systems and we improve what can run closer to the QPU, that compiler will just adapt those changes and you won't have to change your program on the front end at all. So let's take a look at that. So we've got your arbitrary reduction operations remain intact. And I should mention, the way that we do this is with LLVM pattern matching. It's a real common practice. There's all kinds of best practice and prior art here to be able to match patterns within the code and replace them with other code before code generation happens on the end to turn it into whatever executes on the back end. So your arbitrary reduction operations remain intact. You can process your shot counts, or your shot results however you'd like. The shot count itself is inferred from the original program. And that shot count loop uses a shared library call to be able to ship that off to what is the Rigetti C SDK to QCS. This manipulation happens on your program, and then it interns the Quill program as a string within the program, so everything's baked in. Now this program can actually go off not have GCC or Clang don't have to know anything about quantum programming at all. They will happily compile this program in any architecture they support, and you can run that program standalone without having Python there or Qiskit or any of your runtime dependencies. So what we're going to see here, if I'm going to get that to play.
Spacebar.
All right. Okay, so what we see here is that example program that we just saw earlier, but within a more complex classical operation, Ramsey experiment. And this is written in Q#, which, as I mentioned, you can use any language that has a front end for QIR. And we're running this. This was recorded yesterday on our live quantum processor, Aspen 10. And basically, transparently to the user, which in this case is Stefan from Microsoft, he's able to execute his program without any knowledge of QCS or what happens underneath. It needs the libraries at compile time to be installed, and it's performing its optimization now, as if it was just running the Q# directly. And we can see after a few iterations, it actually reaches the expected answer. And the beauty of this is that your programs can get fairly complex without any more work on your part. To be able to adapt those to whatever provider has the library that integrates with QIR. The way that this works, you might ask, well, this is a demo, great. Like, can I do my kinds of programs on this? The beauty of this is that the Microsoft team has built LLVM profiles, which constrain the code that you compile to match the assumptions that we make in our integration. So if you can compile the code, it will run, and you'll get the results that you would expect. And this opens up the door for intercompatibility to anything that targets QIR. It's a common ground for all the many different quantum programming frameworks and languages out there. And we got our correct answer. So, like I mentioned, the QIR allows you to link to high-performance libraries and SDKs that have a C API. It automatically localizes the code because the people writing that backend know their systems probably better than you. If you're trying to run on QCS, we know our systems well. If you're trying to run on another backend, they know it well. Just hand off your QIR and the right thing's going to be done with it. And maybe they'll give you options to be able to tailor it how you want. And then finally, this is low friction. It packages your whole program into one standalone executable, and now it's ready to run wherever. You don't need any other kind of resources at runtime. This makes execution simple and reliable. So with that, back to you, Bettina.
Thanks. All right, these were the 3 hopefully exciting demos that we wanted to present to you today. With this last one, we have seen how we can effectively reduce the time to run algorithms like VQE or QAOA. There's no more Q necessarily in the inner loop. There's no more recompilation. Kalan and team have done an amazing job of actually setting up all these optimizations properly, all the caching nicely. So, week by week as we tried to run it, it ran faster, which was a really nice experience. And with that, I promised I would tell you more about what this QIR Alliance actually is. Now, the QIR Alliance is a joint effort to try to build a stack that actually just meets the need for what we need to do with quantum computing and makes quantum processors shine. So it's launched, it's a project under the Linux Foundation's Joint Development Foundation effort for open standards and open source code. With our work, we've got a couple of goals that I'll briefly restate. For one, of course, we want to reduce the development effort for all parties involved, and we want to promote the interoperability within the quantum ecosystem. Then we aim to build on state-of-the-art compiler tools. We aim to leverage both the learnings and also existing tools and libraries from the high-performance computing space. We want to allow for progressive advances in how quantum and classical interactions can happen at the hardware level in unlocking new capabilities as they become feasible on various quantum backends. And last but not least, we aim to make it easy to connect emerging technologies and thus take full advantage of the unique and distinct capabilities that each hardware backend has to offer. Now with that, I very briefly want to hand the word to the virtual speaker here, who is giving us some insight into how this whole effort relates to the research work done at Oak Ridge National Laboratory.
Hello, and season's greetings. My name is Travis Humble, Deputy Director of the Quantum Science Center at Oak Ridge National Laboratory. It's my pleasure to join our partners in the QIR Alliance today to promote the Quantum Intermediate Representation, a focal point for innovation in quantum compiling and quantum computing. At ORNL, we are heavily vested in quantum computing as a future tool for scientific discovery and innovation. Our priorities include developing the hardware, software, and middleware that drives quantum computing applications in key areas such as chemistry, materials science, high-energy physics, and artificial intelligence. Our research is funded by the Department of Energy Office of Science through the Quantum Science Center, one of the 5 national quantum information science research centers. Among our efforts, quantum compilers play a cross-cutting role that enables computer scientists, material scientists, and device engineers to work together effectively. Working with our QSC partners at Microsoft, we're developing QIR to enable exploration and innovation on novel hardware platforms and high-performance numerical simulators. In addition, with support from the DOE's Advanced Scientific Computing Research Program Office, we're building QIR into the quantum compiler efforts at ORNL. We're implementing these ideas in a language stack built on our signature frameworks, Q-Core and XACC, that enables interoperability across multiple hardware platforms. We then use this as part of the Quantum Computing User Program, where we are using QIR for testing and evaluation of different quantum computing platforms. These studies are critical to our efforts for tracking advances in the field. All of these tools are available online through our open source repositories. At ORNL, we're excited to promote the advancement of the quantum intermediate representation for the quantum community, and we look forward to working with all of you in the future. Best wishes to all, and happy holidays.
Now with that, if you want to learn more, you'll find us on GitHub. Where else? Just go to QIRalliance.org and you'll find examples, getting started material, and more about what we do, how we operate, and how to contact us. Thank you very much, and thank you to all my co-speakers.